Alright, welcome everyone to my talk about practical automated machine learning, state of the art and the recent results. That's me, Tuggener. I will present joint work with a lot of my co-workers. So if you're unhappy with what I say today, feel free to talk to any one of those guys. Most of them are in the room. So, what will I talk about today? First, I will introduce the concept of automated machine learning, so what it is, what kind of the framework is, and also why it exists. I think that's certainly also interesting. Then we'll have a look at the current state of the art, what people are doing, what is working, what isn't working. We have produced some benchmarks in our group. We will have a short look at those. Then I will give some closing arguments and maybe a little bit of outlook, and we should have time for questions if Kurt does his job. So here is a pretty general machine learning setup where you have your data from somewhere, you have your training data, you somehow need to get labels. If you do forecasting, you just have to wait, otherwise you have to hire someone to do labels. You come up with some training scheme, you get a trained model, you deploy the trained model, you take your live data and you get some type of predictions. I assume this is pretty much clear for everyone here, right? Yeah, okay. So what we're looking at today is this training step. What actually happens in practice is that you need a couple of nerd-type people who punch a bunch of different switches and put in some numbers based on gut feeling, based on best practices, and so on and so on. And then they will come up with a setting for an almost infinite list of things you can tune during this training step. And now the goal of automated machine learning would be to come up with a magic box that does all of this automatically. Cool, right? So a little bit more formal definition would be the combined selection model selection and hyperparameter optimization equation. Here, I think this thing really is useless. I need to pick points with my finger. So you basically have two spaces, a model space where all of the different models you could choose live, a hyperparameter space that is conditioned on which model you choose, because deep neural networks and SVMs have completely different hyperparameters, and you have your data space, so all of the data sets on which your system theoretically should work. And then you do cross-validation over all of your data sets and hopefully come up with the best model and hyperparameter setting. That would be the goal in more formal terms. Notably absent would be the training algorithm you choose. There's different training algorithms. Sometimes this is defined as part of the model space, but this is the big guy, right? This definition assumes that you have a vast set of data sets that you can basically just load, and your model will understand them, and there's no missing values and so on. So a lot of people in practice say this is way too narrow as a definition, and people who do more AutoML say, if we relax this, we cannot do anything. So I guess that's the middle ground here. Why do we do automated machine learning? The goal would be to make the people who find all of these values more efficient when the task is hard, so you have faster iterations over possible models because your system assists you with try this, try that, and make them obsolete when the task is very simple. So I guess nobody is going to argue with me that this is useful. Now here, rather than just giving you a bunch of names of systems that people have produced, I am trying to give you some, let's say, dimension along which these systems are designed. First of all, we have optimization. I mean, as you've seen before, the cache problem is you basically look for argmin of some hyperparameter, so it is at its core optimization problem. Now, what people are doing in practice is these model-based systems or Bayesian optimization systems, where you train another meta model that goes along the many data sets and tries to figure out, basically learn how to do it, how to optimize this. Evolutionary strategies is completely different, where you just have a bunch of models and you keep those alive that are doing well, even though this can also be guided by some model-based approach, so these things are not exclusive. You can do tree search, you just can do handcrafted heuristics, you just say, every model that doesn't reach a performance of 0.5 after 20 minutes of CPU time, I just kill it, and there's random search. The most boring and most powerful technique we know in our field. you just throw more compute at it. Secondly, we have meta-learning. So here, we are trying to learn things that are somehow true across the data sets I'm working on. I mean, if you have your data set space in some sense, there should be some things that transition from one data set to another. Here, people are, by data set clustering, I mean people are trying to find metrics to say, okay, these two data sets are similar, or these two data sets are very different. This, for example, could be that you just take a very simple learner, like a linear regression or whatever, and you look at its performance. If it performs very well, the data set goes in this class. If it performs very poorly, it goes in another class. So that you kind of are able to recognize, okay, what type of data sets am I dealing with here? Well, this is more landmarks than clustering. You try, for example, to learn how learning curves, so the performance over time or over iteration, evolves, and maybe you can recognize certain behaviors for certain machine learning models and then see them again on live data, and maybe go from there, training meta models. So this is Bayesian optimization, the models that kind of learn how to do this optimization process, selecting model candidates. It's quite primitive, but just look at all of the models you've trained your whole life and select the best few, and that's your automated machine learning system. You just redeploy those. Pre-trained models. Maybe you've heard of MAML, so you don't just pre-train maybe for ImageNet, but you try to pre-train in a way that you don't overfit to one data set, but you kind of find weights that are somehow in the middle ground across a couple of data sets. And resource allocation can be considered part of optimization. Here we are at the, we look at it through the eyes of, okay, I have 10 GPUs and 1,000 CPUs and so much RAM and this and that, and a week of wall clock time. What do I do now? And the thing here is that you try, for example, to just figure out which models are complete failures. And then these can be stopped early, and you free up some resources to redeploy another guest, essentially. You try to work with smaller neural networks, so you can fit in twice as much inside your GPU. And so on. So here we are looking at it through just how do I use my resources most optimally, which is essentially boils down to explore versus exploit problem that is seen in many fields. Do I just search around my most promising candidates a bit more, or do I just branch out completely somewhere else? Now, state of the art. These are the 4 implementations we have tested. So the first one is from our project partners, called the data science machine. It does a lot of different things, but we just use it as a random search baseline. So we just defined for each hyperparameter a bandwidth from which you can choose, and then essentially fully trained every candidate, whatever that means. So just no early stopping, or just train them for quite a long time. And then there's probably the most famous one, is called AutoSKLearn, which does Bayesian optimization. So it uses, I think, random forests to predict if a model will work fine or not. And this random forest will, of course, in every time you apply AutoSKLearn, this will also be trained simultaneously and hopefully get better. And it will especially get better for the data set you're working on right now, because if it has deployed 10 models, then it knows much more about the data set than when you just give it a data set at first. And in the end, it does ensemble building, which I think is just a free win, something you should always do when you work with these types of tasks. TPOT is something similar, but it uses genetic programming. And then the last one is called Portfolio Hyperband, which we did in our group. Here we just kind of assembled a selection of model candidates. So the models are not trained, but all the hyperparameters are set. And then we optimize them through an algorithm called Hyperband. This one I will explain a bit more because it's quite simple to understand. So on this side, we have basically our portfolio of possible models we might want to deploy. There's one stack of those we have sourced. We used OpenML. They have tons of data sets and trained models for these data sets. And the intuition there was we just looked at all the models that worked well on any given data set, and then we kind of weeded out near duplicates, because we will get a ton of very similar ones, and we wanted to have as broad as possible array of models. And then you spice it up with just some random configurations, because you always want to have randomness in your search. You choose any of these configurations, you train each of those for a given amount of CPU seconds. After that time, you look at the performance of every model, and you just keep the ones, the half of the models which were the best. And you do this until you end up with the best model out of this batch. And you kind of restart, after you ended up here, you restart this process, and you choose less models and a longer CPU time. So you kind of do a search over this trade-off, because some models take a very long time until they get good, and other models are very quick, but then hit the plateau. So you have multiple restarts over this optimization scheme. Here, this is, I would say, a rather simple model-free method. So we don't have any model here that predicts this guy will be very good in another hour of training. We just look at how it is now, and then we proceed from there. And the more time you have, the more random models you would put in here. Because if you have a very short amount of time, you should mostly go from models you know are good, and if you have more time, you should always sample more random stuff. Here are the results. We can see I can see, you probably can't. The bold-faced ones are basically the best performance for a given data set. So we have, every system has worked well on at least one data set, so there is no clear winner. What is interesting here is we have, here you see the time, it's roughly an hour, plus minus an hour per data set. And we also have reported figures for portfolio hyperband after 10 minutes, because it's such an easy, like, quite simple approach that it relies heavily on prior knowledge. It's about the same after an hour or 10 minutes. So if you look at this and say, okay, I have an hour, then you would say, okay, this system is bad. I need to have more randomness in there. I would say this should be clear by now that the design space of possible AutoML systems is incredibly huge, and there is also no clearly superior paradigm. By that I mean is, depending on what you want to do, different methods are better for you. So if you want to spend a lot of time on not so many data sets, you should try some model-based approach that tries to really learn more about the data set at hand. And if you are more in the speedy, if you have to have a model very fast, you should do what we have done here. Just try to learn as much prior knowledge as possible, and then more or less smartly rotate it and see which one ends up to be the best. Anyone who tries to sell you an AutoML system that doesn't use random search at any stage, don't buy it, because in the end it's a very powerful, though boring. Yeah, that's a bit what I said here, that you kind of have a speed versus accuracy trade-off. I put this up here kind of in gold because this always helps. I mean, no matter whether you want to go fast or you want to go accurate, always try to find good prior instantiations. I would say the most powerful thing you can do if you want to do AutoML in practice is really try and figure out what is your dataset space in some sense. Let me give you an example. If you do predictive maintenance, and let's say you have only vibration sensors and temperature sensors, you already know a lot of things that will be very similar for a very for a small or a huge turbine or whatever. So you can already narrow down your metadata set, as it's called, the data set that should represent all of the tasks your system lives in. You can narrow it down tremendously, and this will give you so much more than just going from a baseline Bayesian optimization to the newest and fanciest. Yeah, that's what I said. Spend most of your time finding good data sets that will give a good indication of what the system will work on later, pre-training models, and this is kind of the other side of the coin, building a new AutoML system that kind of gives you a general improvement, irrespective of where it should be deployed in the end, is extremely difficult. I mean, we know from theorems that you cannot find a universally optimal learner, and these AutoML systems are learners that are not biased towards one specific data set, but a sub-region. And I mean, if you think about all the possible data sets, practically every one of those is completely structure-free and just random noise. So we at least condition it on data sets that are somewhat probable, that we can actually measure with a sensor that isn't complete noise. But if you have any information here to make this even smaller, this will give you the biggest gain. And I think that's it. So I'm even 30 seconds too fast. I think we can go to questions.
Very good, thank you.